Good morning, everybody, and welcome to our presentation, which is about cloud-based approach for using Gen AI to support preliminary engineering design. I'm Marco Nunes, and I will be introducing the work that involved the collaboration and the contributions from a wider team across Rolls-Royce and Databricks, and we have the names of the other key contributors on the list. We'll crack on by, first of all, clarifying what is the context and the motivation from the work behind this session, identifying or kind of clarifying also what is the Gen AI technology that we have been taking in consideration and trying to adapt and use it for addressing specific engineering applications. And then move on to the way we have adapted and to the methodology we have pursued in order to make progress against a number of use cases we have identified that are representative of the business needs in our company. After having a look at the preliminary results we got so far, we also highlight and summarize the key enablers and benefits from leveraging on the capabilities from Databricks. And last but not least, we wrap up by having a look at the future work and conclusions so far. So starting with the context and motivation, there are a number of different cases and areas where Gen AI can be used for essentially providing a game changer in the way we conduct a number of tasks and operations throughout the life cycle of our products. In some cases, well, a common denominator is the need, for example, to handle also geometrical representation of our products. And that goes together also with the simulation data that is associated with that geometrical representation. So as a way to identify, quantify the goodness, the performance of our products. Generally, those sort of data are 3D, live in a 3D world. There are some exceptions, and some of those exceptions are some of the tasks in the preliminary design concept phase. And that's the reason this work or today's session is focused on that area. And that's generally the case also because we don't have at that stage all the detail or the information to define in a 3D world our products. How can we use or how we can achieve that? The technology we have been looking at is building upon the work that our friends and partners at the University of Southampton, UTC, has started a couple of years ago now, and is looking at the ability from cGANs or conditional generative adversarial networks as the ability to generate realistic data in different formats. That can be text, can be audio, can be images, can be videos. And that's the technology behind the deepfakes we have seen in the media. The question is, how can we apply that technology to support design tasks in an engineering context? I will not, something that we just noticed from the keynote yesterday from Professor Fei-Fei Li yesterday, where we had kind of a flavor of the latest developments from their team for example, generating images from text. We share sort of similar vision or similar objective. Here, we would like to generate suggestions on viable and optimized design solutions from a given set of requirements, and from that to derive also a prediction that is quantifying the performance or the goodness of those solutions that Gen AI is suggesting to us. So that's where it's not only a means for enhancing and boosting our design space exploration capabilities, looking for different concepts based on a set of requirements, but also having a semi-instant alternative to those expensive traditional simulation studies that we typically conduct during the design phase. I will not go through any details about the training process or the architecture of cGANs. I will emphasize is more the mechanism that the universities attempt to identify in order to do some data fusion that is key for this to happen. So that's merging together the design or the values of the design parameters that define in a unique manner our concepts, together with a pictorial representation of the product. So that's what we see on that image, and is something that will be further clarified in the following slides. Now, why is that important? If we assume that we have a training or a database of simulations with a number of different designs from where we can extract those two pieces of information, that will be the recipe for curating or preparing our training database for the cGAN. And we can do that in a structured manner. We can base or take in consideration the values of a particular output parameter for interest, and use that to essentially define different categories in our training database. And that's what we see on the matrix in the middle of this screen, where we have different columns, and the column on the very left side is giving us some examples of the airfoils in our database that contains, which are kind of defined by a low value of the loss coefficient, whereas the ones moving to the right are having kind of higher and higher values for that output parameter. And by doing so, when it comes to the inference phase, when we can take the trained model and generate, or ask it to generate some synthetic images, we can specify or request the creation in a particular category. Once we have that in place, then we can do the process backwards, extract the information or the engineering data that defines that design, and take that information, conduct a real or an actual simulation, and do the comparison and quantify the prediction error. So that's something that we'll see later on in the results of for the use cases we have taken consideration so far. So before I hand it over to Shiva, please bear in mind there are 5 key steps in the methodology we have been adopting so far. So the first step is the encoding of images, so merging together the information, the engineering information about the design and the pictorial representation of the performance. There is the training of the model, where the configuration of the setup of the hyperparameters and also access to higher computational resources is key. There is the generation of design concepts, where some security aspects will come into play, as will be mentioned later on. Then there is this process of decoding, so extracting the information in terms of values that are associated with the parametric representation of the models of our products, and then running the actual simulations in order to quantify the error in the prediction. So at this stage, I'll hand it over to Shiva for some details about those steps and an overview of the use cases.
Thank you, Marco. So like Marco mentioned, the first thing that we do after we generate the design is to encode the values onto the image. So on the picture you see, on the left-hand side, what we call is like an original image. This image comes straight out of a simulation. This can be any kind of mechanical simulation, CFD, computational fluid dynamics, finite element analysis, or various other simulations that we do to understand the performance characteristics of the design at hand. What we then do is we encode the images with bars and glyphs. What actually we mean by encoding them is for that particular design to be generated, we use a particular set of geometric parameters, performance parameters, environmental parameters. We need that in order for us to, if we had to recreate that simulation in a physics-based environment, we need that to validate our design. So that's what we try to do. So each of these parameters are normalized in a particular range, and then we embed them in the image, which acts as a training data set. Now, there are a few key things that we need to consider while we do this activity. One of the key things is we need to ensure that we don't embed those parameters in encroaching the area of interest. Because at the end of the day, this is a solution that we want to provide our designers to make some key decision making. And if they cannot see that image properly, then they can discard the design while it can be successfully producing the result of interest. So there is some, in order to do this, because we are dealing with thousands and thousands of images, it's not going to be like an ad hoc way. So we have developed some tools that helps the user or anybody who wants to set up a new test case. They can take the design data set and then run it through this tool where it will automatically generate the training data that is needed for the simulation. Once the images are created or the training data set is created, like Marco mentioned, we then put it through our cGAN model that we've developed in conjunction with University of Southampton and Databricks, and then we start generating new designs. So what happens after this? So unlike traditional approaches, if you take the cGAN is very widely used. What is so different in our case is previously, whenever any synthetic image is generated, it has been mostly qualitative analysis of the image, whether does it look like the training data set, whether it is good. But that isn't sufficient for us because we are making engineering decisions based on the result that we get. So this still needs to be validated through the physics-based approach, which is acceptable across the aerospace industry. The aerospace industry does not accept us making any decision based on just the images. So what then happens is once we have chosen a design of interest or the design or an image that we are happy with, we then need to decode them back into the actual parameters that can then be put onto on an existing simulation suite that we have to validate and see whether the result that has been produced by the synthetic generation through cGAN is matching what the physics-based simulation explains. And in here, we've achieved some really good correlation between CFD, which is the physics-based tool, and also the synthetic cGAN image. So I think Marco did touch upon the categories. What we exactly mean by categories is the different type of concepts that we have as part of our training data set. Now, in this case, you can see there is something called a cone angle. So what we mean by cone angle is, is the flow that comes out and then it creates a cone shape. So here you see that the cone angle is a very low cone angle. You don't really actually see a cone. And then that's like a medium cone angle where you see, and then there you have like a high cone angle, which is almost like 180 degrees. Now, how do we embed this information in the image is the glyph that you represent here. So where you have a small cone angle, if you take that like a speedometer, that will be like 0 degrees when it's fully green. And then it's like 90 degrees, and then it's 180 when you got the higher cone angle. So this helps us to differentiate various designs, what it has achieved or which category does it fall into, and then we can make the decision based on those results. Now we tried to apply this on various other components of interest within Rolls-Royce, or as an example use case, not actual components at the minute yet because it's not reached the stage of being applicable to our actual components, but we are trying to run it through various examples and see how much we can, test and verify this. So this was one of the use cases that we developed, which follows a very similar approach, which we previously discussed. However, what we did learn is because of there are so many, to a traditional example of using cGANs, we have various other constraints that it needs to produce a result, that the image needs to produce a result that's correlatable to an actual simulation. So it showcases exactly what, or pretty much what the CFD or the FEA simulation would run. So all the images, in this case, for example, the blocks that we see here, it kind of relates to some of the geometric parameters in there. So if this histogram or that bar says it's 2 millimeters, we should be visually able to see that it's 2 millimeters. If it isn't, then the model hasn't trained very well enough. So with those other examples, they were quite complex in nature. It had a lot of parameters. It had a lot of variability in it. So we wanted to understand because we are quite early in our journey of adopting these kind of approaches to the development of products, we wanted to understand what actually affects the performance, the capability of using this on traditional engineering problems. So we moved back, we took a step back, and we applied it to a simpler use case, which we call here, which is a simple beam where we're just trying to apply a load at the end of the beam and see what kind of bending that we have. This allows us to have a better understanding of it, because these simulations are quicker to run when you want to run it on a physical simulation. And also, the number of parameters that we are playing with is very less when compared to the previous images, which had about more than 20 to 30 parameters. So because we wanted to quite a bit of testing in terms of the effect of architecture, effect of loss functions, effect of database sizes, it wasn't possible to do it in a traditional a desktop-based approach. That's when we kind of joined hands with Databricks to understand the access or how we can access high computing resources. There are a couple of things that we wanted to do, because we work in an environment where data is quite sensitive and we just cannot put it on the cloud. We created this framework along with all the partners that we previously mentioned to see how we can use Databricks, but we don't have to compromise on what data is being pushed forward in the cloud. So before I hand over to Puneet to explain the thing, there are a couple of things that I want to mention, which is more from a Rolls-Royce perspective. For example, the data that we try to push forward on the cloud, we consider what PL909C is an export classification within Rolls-Royce, which basically means that data is a dual-use data. It's more civil-based data or something that can be used across Rolls-Royce. It doesn't contain any any sensitive information. So that kind of data we are allowed to push through to the cloud. Then obviously we just don't want to use it for that particular data. We want to use it for more complex, more sensitive data. So what we then do is, after we train the model using this particular data on the cloud, we get the trained model, and then we do the transfer learning on our local machines. So we ensure that none of the data that is sensitive is being pushed onto the cloud, but we acquire all the capabilities and the learning that can be pushed onto actual sensitive products to generate new designs. Now, just to explain a bit further on the cloud capabilities, I'll hand it to Puneet.
Yeah. So just to give you sort of an example, one of the earlier simulations when I think the team was starting out building the entire end-to-end pipeline, it took around a week to sort of train, where convergence was around 500 epochs, took about a week's worth of training time. And if you look at the entire design approach, it's essentially not fine-tuning, but actual pre-training from scratch based on every new design that comes out there. So they needed a capability where they needed governance as the entire data was proprietary and sensitive, but they also needed a way to sort of scale out the entire design pattern. And that's where Databricks sort of came in and fit very nicely. From a governance perspective, because the entire iteration were based on image data generation, MLflow came into the mix, where we were able to track all the epoch stages, the losses both for the discriminator as well as the generator, not only at an epoch basis, but going down further at every step level. All of the generated image in every epoch was also loaded down into artifacts. So if you wanted to backtrack what data was used with what particular configurations from an MLflow perspective, that's very easy. So if you want to then backtrack to why a particular CFD design choice was taken, you can actually always sort of backtrack to the experiment that it was used to generate. Because we have unstructured data, because it's all images within the Databricks ecosystem, there are multiple ways to handle that. One of the simplest ways is to embed the images as a delta table and then expose that into the workflow programmatically by just using Spark to read the delta table, get the image, and then pass it into the entire computation. But now with Unity Catalog in the mix, we have a dedicated space where you can store not only unstructured data, but any data in the world in a governed fashion vis-a-vis volume. Next slide, please. Thank you. So these were all of the technical space capabilities that sort of made Databricks a nice choice to use. But then the quintessential question was, how can we speed up the training time? And this is where the GPU CPU debate sort of comes into the mix. Within Databricks, because you have the capabilities of not only using GPUs but have a choice of the generation of GPUs, you get incremental benefits of training the same architecture but just on newer GPUs. So for example, if you essentially move from a V100 cluster to an A10 clusters without changing a single line of code, you can get about 3x speed up in your performance. And then that similarly sort of carries over to the A100s. And pretty soon within Databricks, we are also going to get availability for H100s, right? Because we have this entire distributed job format, one of the aspects is finding the exact search space which gives you the best generated images. And this is where, as the next stage of the project, we are actually working on how we can create a completely automated hyperparameter optimization architecture, where, again, we can use any sort of tools that we need, but we are sort of zeroing on using Ray for that particular process. But all of that can be sort of automated and serialized within the Databricks environment. So the things that we wanted to sort of tick off from the end-to-end perspective, hyperparameter optimization was available within the ecosystem. You can either use Spark, you can use Ray. Both of them are generally available in the ML runtime. Parallelization is, again, the bread and butter of the entire Databricks universe. From a costing perspective, now this is an interesting point, because we were able to speed up the iteration from 7 days to actually down to about 4 or 6 hours for a training run. And within the cloud ecosystem, you only pay for the compute resources. You actually get benefits of using better architecture whilst lowering down your cost. And then all the other governance capabilities such as traceability, access control, data pre-processing, all of them were readily available out of the box by using a combination of Unity Catalog, the entire jobs API, and using MLflow for model management and model tracking. And I'll now pass it on to I have one more slide. So the other interesting point was, we need a lot of data to start creating GANs, but we needed to create empirical rules to automate this process. So going back to a full-fledged process of what Shiva shared, we needed an aspect where users can put in the information, generate the data, and then just churn it through a pipeline where they have their own generative model created in a bespoke fashion. So for that, we came up with these empirical rules where, from a training cost perspective angles, anything less than 0.5 million image set, you could just run it off a single GPU. But the moment you wanted to sort of increase that, you then could move on to a single node multi-GPU architecture. And only if you wanted to do a hyperparameter search space analysis, do you go for a multi-node cluster. Now, setting this up in a native cloud environment is challenging, but in Databricks, it's as simple as just doing a config switch. So that was the added capability that we were able to build in to this entire end-to-end pipeline. Next slide. Perfect. I'll now hand it over to Shiva to sort of talk about some of the detailed training results.
Yeah, I've got it. Hi, yeah, so what we did, after we set up all the cloud, we did a ton of experiments. So to do this set of experiments, we first created our training data set for the beam, which we earlier discussed. So initially, we had a training data set of 98,000 images or 98,000 design points. As you can see on the graph, some of the design points, or most of it, kind of lay within the first 10 along the y-axis, the value of 10. And then it becomes quite sparse. So we thought, okay, we wanted to see what will happen if we try to apply and run this through a training model and what kind of result we would get. And the results were quite obvious. You can see here, it was not performing very well. Now, before I get into the results, a couple of things that I want to mention here. The diagonal line actually represents 100% correlation between the actual value and the predicted value. So if there was a design point where your actual value matched the predicted value, then they would sit on the diagonal point. So anything that goes out of space is basically, there's some induced error in it. What was interesting here is with the 98K data set, for the first three categories, you didn't see any change. It's almost like it was like a flat line. And kind of understanding the data set, and this is where data curation becomes extremely important. What we realized was because we were trying to run, there were high density points at a certain area of the place, and then there were sparse points in the other part of the design space. When we normalized those ranges and then we started to train, essentially the output value that we get, which is what this is, here you'll see most of them will almost be like green. There wasn't any change because you're converting a numerical value onto a pixel value. So if you have a variation of second decimal place, that would never have a huge impact in the pixel representation of it. And that's what happened here, and that's what you see, that these values were, the results from that particular training data set wasn't very good. So what we then did was we kind of removed all the values that, we put a hard line to say, okay, we're going to normalize it within these ranges. So now the data set kind of reduced to 63,000 images. Now in this result, we can see a lot more correlation. We can see there's variance, there's almost like a beehive when it comes to generation of points, and then also they almost sit on the diagonal line, which is where we want. That kind of explains to us that our model is trained very well. The difference or the change between the actual and the predicted value is not huge enough, so we have a bit more trust in the model. Now, this was with respect to the database or the size of the data and the curation of the data. There's another interesting result that came across from this work, because there's always talk about, when we started off with CPU because we were testing out the capability. And then we were, when we spoke to, when we looked at literature, we spoke to people, they said GPU is the thing because GPU goes, it's faster, it's better, it can start generating the designs. We tried a few examples on our desktops or on our local machines, and we always saw some variation in the result where the CPU performed better than the GPU. And we wanted to check this out even on like a higher computing resource and see what happens. And here you see an example. These are the two experiments. The experiment is exactly the same in terms of architecture, hyperparameter tuning, the versions of PyTorch we used. We didn't change anything. We just changed from CPU to GPU. The CPU results is something we would expect, which is kind of a beehive. It's on the line. There is some variance because this model is not tuned. But then the GPU, you see it's a flat line. Now, we don't have the answers for this. We are still trying to understand what could be the problem or the cause for it. Because in other examples or if you take the traditional literature approach where they've used MNIST data set, it doesn't really matter because they're looking at a qualitative analysis of the image. Whereas we are trying to do is we are validating with actual simulation result data. And we see that there is significant hindrance in terms of the GPU. That doesn't mean the GPU does not work. It might mean that the architecture for the GPU has to be slightly different to the CPU. This is something we need to verify. But then this is one of the interesting results, and I think it was good to share it to the floor. And if somebody has any views on this, that's most welcome for us to improve our understanding of this. So what are the current challenges that we have, or what we are looking forward to in the next coming months? There are a few things that we want to address as part of the exercise that we've done till now. So we want to understand, because when we read through the literature, how could we improve the performance of these models, or how could we make it better? There are a few things that came up to play. One was the architecture. People were talking about the architecture, but not in a huge sense. The emphasis was mostly given to the loss functions, using different kind of loss functions that is available out there, from KL divergence to Wasserstein with gradient penalty, Jensen-Stratton, you name it, it's there. So they wanted to, that was the first, where they alluded to see if you change your loss function, that could definitely improve the process. The other thing is about configuration, because there are various different parameters that we have in here, from learning rates to epochs to the number of filters, and how do you, the depth of your network. There's tons of it that we could play with. So we want to understand how each of them have an impact and how does it correlate to the data set that you're training. That's something that's very important, because our, we would apply this to a wide variety of applications if successful, which can go from smaller products to a wide range of products. So we need to understand all of this before we can say we are ready to apply to a wider case scenario across the business. Finally, so just for future work, what we've done, so we are kind of investigating on the best practices and the setup for these models. What we've also done is we've moved away from the dimensionality limits. We are now actually looking at training 3D models, not just 2D models, because the products and everything that we develop are 3D in nature. They are not 2D, they are not images, they are actual physical products which are 3D. I mean, when we came into this conference, and we spoke to a lot of people, data here, whenever we spoke to anyone, data is assumed to be numerical, text, images, but then there's wide variety of data which we deal with is completely 3D. You can see we've tried to apply this on a simple problem, and we've got successful results. And also, we are trying to push the boundaries where we actually modeled a blade as well. So that's where we are. That's where Rolls-Royce is going in order to exploit this capability. Long term, we want to. What we also want to understand is there are when we create this training data set, not all the solutions or all the experiments that we create would converge or would provide a successful run. It would also provide some unsuccessful solutions or unconverged solutions. For example, if the parameters are not within a range or a physics to actually hold good, then the simulation would fall through. But it is important we embed this knowledge, because then we tell the neural network not to look at certain places rather than keep on looking at every single place possible. This helps us to get to a solution much faster and better. But also, as we said in the previous slides, we have one glyph which represents a particular output or a particular objective which we are trying to maximize or minimize. When we build products, we don't work with one particular objective. We have more than n number of requirements, and which can be conflicting to each other. Like, for example, people are trying to reduce the weight, but trying to increase the efficiency. They are conflicting one another. How can we handle those kind of multi-constraint objectives or multi-objectives or constraints and the design metrics, and produce a solution that is overall optimal, not just optimal for a particular facet of the design?
Okay, so thank you very much for your inputs and questions.
What do you do?